So we're trying to understand why we get this sort of pattern with diffraction. If you've got a slight slit and we are shining a light or any kind of wave through that slit, we find that it spreads out like this. It spreads out like this if the gap, little d, well, that's little a, but if is approximately equal to the wavelength or about the size of the wavelength or less, then if that's the case, then you end up getting this pattern here. But also, if you were to get a screen, let's say we do it with light, and we get a screen, and we look at how the light spreads out across the screen, you'll actually see that there's a bright fringe in the spot, but then it doesn't actually just get less and less bright, but you get these fringes, these points of relative brightness and relative dimness. So we're going to try to understand why that is the case. If we look at this diagram, we notice that they've called this angle theta and this one theta apostrophe. They're saying that these two angles are not actually necessarily the same, but we're saying that for some reason they're approximately the same. And then we've got this leads to various other approximations up here, which we'll come to later on. So if I redraw this and just take parts of this diagram out over here, and we imagine that we did it 1 meter away, where that was 15 degrees. Because oh yes, and also we need to explain what is this bit here, what is this dotted line here. They haven't drawn it as a dotted line there. Oh, they have actually. Yeah. And they've labeled it as delta. I've labeled it as just, path difference. So the path difference is the difference. So basically from capital A to wherever this point here is, we're saying that's 1 meter, for example. That won't be 1 meter then. Let's forget about that. Let's say that's traveled 1 meter. This will have traveled further than a meter, okay, because it's further away. This is a more direct route to that point on the screen. This one has a less direct route, so it would have to travel further. And the extra difference we call the path difference. So we'd say from this point onwards to the wall, then it's the same. And the extra bit that it had to travel, we call the path difference. So then we look at and then we just draw this dotted line to show how we'd chop up that triangle. Okay. Now we can say that from here, and then from here to there on the screen, and from here to there on the screen, they're the same length now, and so that's an isosceles triangle. I said that in our first situation, let's imagine it was 15 degrees. So the remaining two angles would be 82.5 degrees because it's an isosceles triangle. And so those two angles must be the same. 180 minus 15 is 165. So the remaining two angles must add up to 165. And because they're the same, we can divide it by 2 and we get 82.5 degrees. Then we can see this angle on a straight line. This angle here is actually going to be equal to 92.5. So they're both a fair distance from 90 degrees. But as you were to decrease the size of this angle, then all these angles over here get closer and closer to 90 degrees. Now, so in the diagram just to the left, they labeled this angle as theta, and this angle here, I believe it's this way around. Let me just double check. Yeah. And that angle there as theta apostrophe. So as this angle here approaches 0, gets smaller and smaller, then so does this angle. And so basically when theta is very small, then theta, so when theta is very, very tiny, then also theta apostrophe is very, very tiny. And so they both are approximately equal to each other. That's essentially what they're saying. And also for that, when that angle is very, very tiny, then the distance they've travelled is actually approximately the same as this distance, d. So for these small angles, then this 1 meter is going to be roughly equal to capital D. So I'll get rid of that now, and we'll imagine it was like 0.5 degrees. And then obviously these ones aren't 82.5 degrees anymore or 97.5 degrees, but they're much closer to around about 90 degrees, all of them. Well, that one, and this one. Okay. Now, because of that, these two blue lines, although they converge eventually, they can be treated as parallel lines in some ways. Obviously, they're not parallel lines; they do converge to a point, but because the angle's so tiny, then you can use various assumptions to treat them as parallel lines. So, because we know that let's have a look at this other approximation over here. Sine theta, it says tan theta is approximately the same as sine theta. Well, why is that? Well, if we have, so what I'm going to do is I'm going to draw out my triangle, which is, this triangle here, right? So I'll draw out both triangles. We've got this triangle, that's angle theta. That's the point on the screen where they converge. And these are approximately 90 degrees. So you could say, if I looked at from this point of view, let's imagine that, so let's say that's our 90-degree angle. Then this would be the opposite, and this would be the hypotenuse, and this would be the adjacent. So let's do sine theta because we're comparing that. So sine theta is equal to opposite over adjacent. Sorry, hypotenuse. And in this case, the opposite it's labeled A there. We've labeled it D. Is D, and the adjacent is actually the capital D. Okay. And so that's the splodge on the wall. Okay, hang on. Oh no, sorry. That's the wrong angle here. So let's rotate it. Let's rotate this triangle here. So basically, we've got this triangle here, where that's theta. This is Y. I believe in your textbook it's W, and then that's D. And because this angle is very, very tiny, then we can just say that sine theta is opposite over adjacent, which is W over D, right?
Mm-hmm.
And let's move that over there. Now we take the second triangle, this one over here, and we say that now we've got theta apostrophe, and this is the path difference. They've used delta. Let's just use their symbol. They've used A. In your textbook, it's D, which I've labeled here. And now that's the right angle on this triangle. Again, remember, it's not really a right angle. We're approximating because it's a tiny angle. Sorry, this is a tiny angle, and so these two end up being roughly 90 degrees. So that's the approximation we're doing. It's good to know that what the approximations are, but then apply them. But don't lose track of the fact that it is an approximation, because when you get to larger angles, the approximation doesn't work anymore, and they will question you about that. So now we got tan theta apostrophe is equal to opposite over adjacent, which is the path difference, over D. Now, because these thetas are are roughly equal to each other, then we can say that tan of the other theta must therefore also equal the path difference over the gap between the two fringes. And so, therefore, tan theta. Oh, and also because tan theta is so for these small angles, we can say that tan theta is roughly the same as sine theta. In a nutshell, if we draw the diagram of sine theta, you can see it starts at 0, and the same with the graph of tan theta. It starts at 0, and so tan theta is roughly equal to sine theta, and it's also roughly equal to theta because theta is very, very tiny. And so you can actually say that theta rather than sine theta is equal to w. Well, they said y, we said w over d, so we could say that theta is equal to w over d, but that's also equal to the path difference over d. So you end up with that situation there. Now, again, they're using different symbols here. So we use w, so w is roughly equal to. Forget about the m right now. We're talking about the first fringe. So we just rearranged it here. So let's have a look at our symbol over here. We got w over capital D is equal to. We should probably always keep using the curvy equal sign to remind ourselves that we are approximating the whole time. And then by rearranging it, we've got w is roughly equal to that over d. And then multiplied by capital D. Okay, and because their w is y and their little d is an a, yeah, it's the same. Does that kind of make sense?
Mm-hmm.
I think the last little bit, my explanation around here was a bit shaky. But hopefully you can make use of everything else that I've said and rewatch it. Okay.